Okay, so we have been discussing the kinetics of phase transformation, and in this context, one very important concept which has great practical utility is what is called as the time temperature transformation diagram. In short, this is called as the TTT diagram. This diagram is also called as isothermal diagram, isothermal transformation diagram. Now, what is this isothermal transformation diagram or the TTT diagram? Well, in this diagram, very neatly, given conditions of temperature of transformation, it can tell us at different times how much, what is the fraction of the transformed product. In order to construct this diagram, one starts, let us start with the Avrami function or the Avrami plot of f versus t, fraction transformed versus time, which we saw in the last lecture is a sigmoidal curve, something like this. Let us say that I have plotted this particular diagram or this particular curve or this particular set of data points from an experiment at a temperature T1. So, let us say this particular curve is plotted at temperature T1. Let me set the start and the end of the transformation. Well, we can not really set start of the transformation at 0. It's not, it's very difficult or almost impossible to measure the start of a transformation, but one can decide on a small number as the start of the transformation. Let us say, we say that when the fraction transformed is 0.01 or simply 1% fraction transform, let us consider that as the beginning of the transformation, and let us consider the end of the transformation as when the fraction transform becomes 0.99 or simply 99% of the transformation has taken place. So, on this sigmoidal curve, I have 2 points. The start of the transformation, let me call that as point A, and end of the transformation, the point on the curve, let me call that as point B. Now, what I do is side by side, let me draw this time temperature transformation diagram. So, vertical axis is temperature, the horizontal axis is time. In this, let us select, let me first put down on this the temperature TR. So, let us say we are looking at a phase transformation of alpha going to the beta phase. So, this TR is the transformation temperature. So, temperature above this transformation temperature, we have only alpha. It is only when the temperature goes below the transformation temperature that beta will start to form. Now, on this curve, I want to plot these points A and B. So, let us say this is my temperature T1, and on this, let us say point A is whatever time that is here. So, what same time I plot, I make this point A here. I'll call this as point A. Then on the same temperature T1 line, I'll have another point B. So, what these 2 points are telling me is that if I keep the temperature, transformation temperature as T1, the transformation is 1% complete when this much time elapses, and then when further this much time elapses, the transformation is 99% complete. Now, let me consider another, we go down in temperature. As we go down in temperature, as we have already seen, initially when we are, this temperature T1 is quite close to the transformation temperature, so the kinetics will be slow because the nucleation rate will be low, the growth rate would be low. But both of nucleation as well as growth go through a peak as the undercooling goes up. And let us consider another temperature T2 where the kinetics have now are at a peak. As a result, I will have a second curve showing much faster kinetics, and this is at temperature T2. Again, I can mark 2 points that this much time is required for 1% transformation to complete, and this much time is required for 99% transformation to be complete. So, here let us say the temperature T2 is somewhere here, and I make a plot, copy these 2 points on this diagram. Let me call these points as point C and point D. So, point C will of course be somewhere here, and so let me call this as point C, and point D would be at a time earlier than point B, but greater than point A, so that point may be somewhere here. So, let us say this is points, these are points C and D. Now, let us choose a third temperature where the undercooling is very large. As a result, again the kinetics slows down, and the transformation curve at a third temperature T3 looks something like this. So, this is now at temperature T3. So, I have again 2 points for 1% transformation complete and 99% transformation complete. I will mark them as points E and points F. So, I have now points E and F. Correspondingly, on this diagram, I note this T3 as the transformation temperature, and point E, let us say maybe somewhere here, at point F is, let us say somewhere here. So, I have these points plotted in this fashion on this diagram. Now, imagine that I can repeat this exercise for many other temperatures between T1 and T3. So, I will have a set of points, and I can join all those points. So, I can join points A, C and E because they all correspond to 1% transformation complete, and I can join points B, D and F to indicate 99% complete. So, this is 1% transformation complete, this is 99% transformation complete. So, all the points on this curve are for 1%, all the points on this curve are for 99% of the transformation getting completed. Similarly, I can choose other fractions. For example, I can choose 50% complete. So 0.50 on this curve. So I have 3 points to be plotted there, P, Q and R. So point P is for temperature T1, so point P will be here. Point Q is for temperature T2, so point Q will fall somewhere here, and point R would fall on the temperature T3 line. And one can join these 3 points as well, and I will get on this diagram the 50% transformation complete line. Similarly, one can have lines for other percentages of transformation. This constitutes what is called as the time temperature transformation diagram, because in one single diagram I have very neatly put down amount of transformed product given a temperature of transformation and given a time. So, for example, if I want to find out at now a temperature, let us say at temperature T4, what is the situation? Well, the situation is that it will take this much time for the transformation to get completed, or only 1% transformation to take place, and it will take this much time for 99% of the transformation to be over. Similarly, one can find from this diagram for other temperatures what is the rate at which the transformation is taking place. Note from this curve that they are both, all the curves that are drawn are in the shape of a C. So, many times such diagrams are also called as C curves. And the reason for the shape of the curve being in a C shape should be clear, that for small undercoolings the transformation rates are slow. So, it takes much longer time for transformation to start and end. At very high undercoolings or at very low temperatures, again the kinetics is slow. At intermediate temperature the kinetics is fast, and at temperature T2, the way I have drawn this, the kinetics is the fastest, or there is a peak in the kinetics. Now I will a similar kind of, now these kind of curves can be drawn for different transformations in different material system. Suppose we take the example of a eutectoid steel. So, taking the example of a eutectoid steel, that is roughly 0.8% carbon, and let me sketch the diagram for the TTT diagram for the eutectoid steel. That's, I'll put down the vertical axis as temperature axis. Somewhere here is the 723 degree centigrade line, or the eutectoid temperature line. Above this temperature we have all austenite in the steel, and below this we would have ferrite and cementite. The C curve for this, I will just roughly sketch it. So, let me put time here. Okay, this is a very rough sketch I have drawn. So, this represents the start line of the transformation, this represents the end line. End of transformation, somewhere here would be the 50% line. So, out here is austenite gamma and out here is alpha plus Fe3C, ferrite plus cementite. For many systems this diagram would be sufficient, but in the case of steel we have some more points on this diagram. Suppose I were to cool from austenite, so if I cool down let us say to 500 degree centigrade rapidly and then hold it here, then the austenite will start to transform to ferrite plus cementite in pearlitic morphology, and end of transformation in about let us say about 100 seconds or so at 500 degrees centigrade, and the transformation starts just in a few seconds. If I am somewhere at 700, you can very clearly see that this transformation will take a much longer time to start and a much longer time to end. Similarly, if I go down to about let us say 250 degrees centigrade, again the transformation will take a much longer time to start and end. What would happen if I just continue to cool down without touching the C curves? Then in this case, in the case of steel, austenite gamma transforms to what is called as martensite, which is a metastable phase and its crystal structure is body centered tetragonal. This transformation is a diffusionless transformation and it takes place through a shear mode. However, this particular transformation will not be discussed in this course, it is beyond the scope of this particular course. But on the diagram we would have a martensite start line, it's called as MS, and we would have a martensite end line, or let us say M90 line, that when it reaches this, the 90% of the martensite would have formed. And the other thing to note is, incidentally I should write this also, vertical axis temperature is in degrees centigrade, the axis is time in seconds and it is log scale. That you can make out by the way I have put the times on the horizontal axis. So, you can see from here that if you want to design a heat treatment, from this diagram will tell me that at different temperatures how long it takes for the transformation to start and end. Other thing that I have not pointed out here, and as such a little bit out of the scope, is that in the upper part of the C curve, in this particular case we get pearlite morphology, or simply pearlite, which is alternating layers of ferrite and cementite. The lower part of this particular C curve we get bainitic morphology, or simply called as bainite, which is again consisting of ferrite and cementite. However, the mechanism of transformation of pearlite is different from the mechanism of transformation of bainite. However, we will not be discussing these mechanisms here. Now, the TTT diagram as such you have seen is also called as an isothermal transformation diagram, which means that the transformations are done at a constant temperature. However, for many practical applications, we have transformation is taking place as the temperature is continuously cooling. In that case, the TTT diagram directly will not be able to tell us when the transformation will start or the kinetics of the transformation in that case, where things are being continuously cooled. And in large number of practical cases, that would be the situation where the cooling is taking place continuously. However, in many cases we also do isothermal transformations in the industry. So, we also have something similar to the TTT diagram to take care of the continuously cooled material. In the case of the continuously cooled material, we have what is called as continuous cooling transformation diagram, or simply CCT diagram. So, what is the continuously cooling transformation diagram? Again, you will see it will be in the form of a C curve. This is temperature axis, this is the time axis. However, to read such a diagram, suppose I cool continuously, my cooling curve may be something like this. So, this point now will tell me the start of the transformation, and this point tells me the end of the transformation. Similarly, if my cooling goes something like this, then again it is telling me the kinetics of the transformation. Or if I cool so fast that I go down, then no transformation will take place, and if it is a eutectoid steel or any other steel, then we may end up getting martensite. If this is austenite here, then out here would be alpha plus Fe3C, out here is austenite, and then you will have the martensite start line over here, and you will get martensite if the continuously cooled material does not touch the C curve. And this diagram can be derived from the TTT diagram, but however we will not be doing this in this course. With this I stop here.